We're going to verify Stokes' theorem for the vector field f of x, y, z is equal to negative 2yzi plus yj plus 3k. Whoops, that's plus 3xk. And s is the part of the paraboloid z equals 5 minus x squared minus y squared that lies above the plane z equals 1, oriented upward. The instructions verify Stokes' theorem really mean to show that if we compute the line integral over c of f dot dr, then we get the same answer as the surface integral over s of the curl of f dot ds. In order to find the line integral over c of f dot dr, we need to know what c is. C is the boundary curve for the surface, the paraboloid, which is cut off by the plane. So for that curve of intersection, we have that z is equal to 5 minus x squared minus y squared, and we want to know where that meets z equals 1. So setting those two equal to each other, we have 1 equals 5 minus x squared minus y squared, or x squared plus y squared equals 4. This is a circle of radius 2, but has a z value of 1 throughout the circle, right? It's elevated on the plane, z equals 1. And so our parameterization in terms of t is going to be r of t is equal to 2 times the cosine of t, 2 sine of t, 1. And folks, we're using t here and not x and y because we're looking at the line integral over c of f dot dr. This should have only one dimension because dr is going to include a dt. So we're limited to one variable for the parameterization. R prime of t is, of course, negative 2 sine t, 2 cosine t, 0. And now we need to express f in terms of r. And f is negative 2yzi plus yj plus 3xk. So substituting our values from r into x, y, and z as appropriate will give us that f of r of t is negative 4 times the sine of t, 2 times the sine of t, 6 times the cosine of t. The line integral over c of f dot dr is equal to the integral from 0 to 2 pi of the dot product. So 8 sine squared of t plus 4 times the sine of t times the cosine of t plus 0 dt. Applying a power reducing formula and using the power rule, we get that 8 sine squared of t becomes 4 minus 4 cosine of 2t, and then integrating we get 4t plus 2 times the sine of 2t, excuse me, that was minus 2 times the sine of 2t, and then the power rule here is going to give us 2 sine squared of t as we integrate 4 sine t cosine t. Evaluating from 0 to 2 pi, as it turns out, all the sine of 2t's and the sine squared of t will all go to 0, and we end up with a value of 8 pi. For the surface integral over s, the double integral of the curl of f dot ds, we need to do a little bit of work. Recall that f of x, y, z is negative 2yz, y, 3x. And so the curl of f is equal to the cross product ijk, partial with respect to x, partial with respect to y, partial with respect to z, negative 2yz, y, 3x. And you can confirm that the answer of this turns out to be 0, negative 3 minus 2y, 2z. S, recall, is the paraboloid z equals 5 minus x squared minus y squared. Cut off at z equals 1. We'll deal with that in just a bit. But this gives us a parameterization. R of x, y is equal to, since it's a function, our parameters are x and y. So x, y and then 5 minus x squared minus y squared. We can either find the cross product directly, or remember that Rx cross Ry is going to be the negative partial of g with respect to x, and so 2x, comma, the negative partial of g with respect to y, and so 2y, and with an upward orientation, we want z to be 1. The k component to be 1, I should say. Our surface integral then becomes the double integral. We'll get to the limits in just a minute, but we're looking at the curl of f dot ds. The curl of f is, as we said, 0, negative 3 minus 2y, 2z, dot, and ds is going to be 2x, 2y, 1 dA. Now before we get to those limits, we do have a problem here because we've written 2 as z, but we need to have everything in terms of only two variables, dA. We have a double integral. Therefore, we're going to replace that we're going to replace that z with 5 minus x squared minus y squared. So that's how we're using the function and replacing 2z. As far as dA describes basically the area of the region D. The region D is a projection in the xy plane at this point, and it's a circle of radius 2. A disk of radius 2, rather. We're talking about the entire, the circle and its interior, right? So I'm just going to write D here, and folks, with a disk of radius 2, we're going to go into polar coordinates. Forming the dot product and simplifying is going to give us negative 6y squared minus 2x squared minus 6y plus 10 dA. And converting to polar, now we're going to be looking at the double integral, first from 0 to 2 pi, and then from 0 to 2. Negative 6r squared sine squared of theta minus 2r squared cosine squared of theta minus 6r sine of theta plus 10 r dr d theta. Again, we have r dr d theta because we did actually convert from xy into r and theta. After integrating and substituting with respect to r, we get the integral from 0 to 2 pi of 20 minus 24 sine squared of theta minus 8 times the cosine squared of theta minus 16 times the sine of theta d theta. At this point you're saying, well, how was I supposed to do that so quickly? You weren't. You were supposed to pause it, and you could at this point and verify that this is what you get. Applying power reducing formulas and integrating will give us 20 theta minus 12 theta plus 6 times the sine of 2 theta minus 4 theta minus 2 times the sine of 2 theta plus 16 cosine of theta, evaluated from 0 to 2 pi. All of the instances of the sine of theta, sine of 2 theta, cosine of theta will go to 0, and we will end up with that same 8 pi.